In this second section about instrumentation, we will talk about the address sanitizer. Address sanitizer, or ASAN for short, it's a tool designed to help catch memory-related bugs that can be difficult to identify. These are issues like buffer overflow, where a program writes data past the end of a memory buffer, or use after free errors, where memory is accessed after it's already been freed. Normally, these types of bugs might go unnoticed during development because the program might seem to run just fine, but they can lead to serious security vulnerabilities or crashes down the road. What ASAN does is to instrument your code in a way that actively monitors how memory is being used while the program is running. It places checks around every memory access, so if your program tries to read or write to memory in an unsafe way, ASAN will catch it immediately. The great things about ASAN is that it integrates directly with compilers like LLVM or GCC, meaning you can enable it pretty easily during the compilation process. Other key characteristics of ASAN are that it's already built into LLVM and GCC compilers, and compared to other memory debugging tools, it's lightweight and efficient with an average slowdown of the instrumented program of 2, and it does not produce false positive. If you see one, look again, most likely it's a true positive. The way ASAN works, it's both powerful and straightforward. Essentially, it redefines how memory is laid out during execution. Imagine it like this. When your program allocates memory, ASAN adds small buffer zones called red zones around the actual memory block. These red zones serve as a guardrails, so if a program tries to read or write outside the allocated memory, ASAN immediately notices the violation. But it's not just about padding memory. ASAN also instruments the code, meaning it adds checks before and after every memory operation to make sure you are not stepping out of bounds. Behind the scenes, ASAN manages something called shadow memory. This shadow memory helps to track which parts of the program memory are valid or invalid. And if the program touches invalid memories, like a red zone, ASAN catches and throws a detailed error report. In short, ASAN constantly monitors memory access and stops the program when it detects any suspicious or invalid behavior. Let's look a bit deeper into how ASAN actually achieves this. First, we have the concept of shadow memory. Think of shadow memory as a smaller map that mirrors your program's memory. Every byte in your program is represented by a corresponding byte in this shadow memory. These shadow bytes are marked to indicate whether the memory they represent is safe to access or not. Now, when your program runs, ASAN places red zones around each memory location. These red zones are just padded areas that ASAN marks as invalid in the shadow memory. If your program tries to access one of these red zones, ASAN immediately catches it, thanks to the shadow memory tracking. To make this all work, ASAN instruments your code. During compilation, it adds additional checks before every memory operation. These checks verify if the memory being accessed is valid by looking it up in the shadow memory. If the memory is invalid, whether it's in a red zone or freed memory, ASAN triggers an error and provides a detailed report about what went wrong, including the type of error, the memory addresses involved, and even the stack trace of the fault instruction.